We listen from Fabien Montiel on theoretical framework for the emergent flow size distribution, the case for log normality. Fabien, how are you? When you're ready, please share
Good.
your screen.
Yep. Can you hear me?
Yep. Crystal clear. Yeah. Okay. Over to you, Fabien.
All right. Thank you, Pat. Yes, nice to hear from you. And thanks. Thanks for the opportunity to give a talk here. And sorry I couldn't make it in person. Hopefully we're going to have a bit of discussion after that. So I just want to apologize also in advance. It's a very similar talk I gave a couple of months ago in Cambridge at the Isaac Newton Institute meeting on sea ice. So if you've already seen that, then it's an opportunity to see the same thing twice, basically. But it's based on work I've done with my PhD student, Nico. So most of it is actually led by Nico. And very conveniently, he's sitting right next to me right now. So if I have any question, I'll just give them to him. I also want to acknowledge funding by the Antarctic Science Platform, the Deep South Challenge, and the Marsden Fund for this research. So, okay, so we've just heard about flow size distribution. So I don't think there is much need to go at length on what it is, and it was also mentioned in the last couple of days. But the idea, of course, of the flow size distribution is that we try to estimate the probability density function of flow size in a given sample, and usually it's obtained in two steps. So there is an image processing of some aerial images, either taken by satellites or drone footage, like we've seen. And from that, there is a flow size which is extracted, which can be defined in different ways. But the point is that it is then the distribution can be plotted. And even though in the previous talk, Eli has mentioned the actual density function, in the literature, most of the time you will see cumulative number distributions plotted from image analysis. And what has been used from the very start, from the very first observation of flow size distribution to understand the FSD is the power law. So the power law is typically fitted to observational data, and that's been done so since the early 1980s. And I also wrote here a variation thereof because they are sometimes it's referred to as a split power law. So there's two different regimes for small flows and large flows with two different powers. And there's also the truncated power law. So there's different types of power law which are used, but the power law is usually the unifying theme here for the flow size distribution. And that's really what I'm mainly going to talk about here and trying to maybe question the validity of this power law formalism. But I guess one of the reasons it's been used that much is that there is a really nice way of justifying its emergence from a fairly simple process. And it's a sort of a cascade fragmentation process, which can be described as follows. So, and that's taken from this Toyota paper here from 2011. And the idea is that you start with a flow with a given size, D, and then you just iterate and break it apart at each step. And then at each step, so the flow breaks in n equal pieces. So here, in this case, would be 4 on the diagram on the right here, but with a probability P. But the key thing here is that if a flow is not broken at a time step, then it cannot get broken further in subsequent time step. And that's an important assumption here. And when you follow this procedure, then you can prove that this leads to scale invariance and therefore the emergence of a power law with a power here, gamma between 0 and 2. So that can be understood through that process, the emergence of the power law. And that's been observed, like I mentioned, in many different data sets. So there is a really nice study by Stern et al. Here in 2018, which essentially does a meta-analysis of many different observational studies of power laws fitting to flow size distribution. And actually, they found a range of powers here between 0.5 and 3, so slightly higher and broader than the one given by the theory. And the standard way of extracting it and And here I want to also emphasize that these are limitations, and that first, these are usually done on a cumulative distribution instead of the probability density functions. Usually it's done through least square fit instead of the maybe more powerful maximum likelihood estimates. And the goodness of fit is also not well estimated consistently. And so the problem here is that even though that's been observed and done for a large number of field studies, there are a number of lab experimental and also modeling studies which do not support the emergence of this power law. And that's what I want to talk about next. And the first one here, there was a couple of experiments done in the last few years by Herman et al. And Passerotti, who I think talked yesterday. And here are the distribution, the FSD plotted in each of these two experiments. And if you look at them, especially for the Herman et al. Here, so even though on the right here, these are the cumulative distribution plotted, it may look like a split power law with two different slopes. If you actually look carefully at the probability density here on the left, then there is a better way of understanding these distributions as the weighted sum of two underlying distribution. One, which is actually what they refer as a tapered power law, which describes here mainly the small flow size. And then you have here they fitted the normal distributions for the middle flow size. And here you can see on the right here, so these do not look at all like power laws. There is clearly a mode in both cases here. I think D1 and D2 represent the minor and major axes here of the ellipses they use to fit the flows. Now, of course, we've just heard from Eli, so I'm not going to talk about that more, but we've seen his distribution, and these clearly do not look like a power law. And what I really want to highlight here is that, again, we can see the emergence of a mode in these controlled experiments. And here I'll just plug in some results from a few years ago that I did with Vernon, where we did some modeling, actually trying to use a three-dimensional wave scattering model and then break flows iteratively and see the kind of size distribution it generates. So the idea is that we start with a very simple distribution of ice flows. I think all the ice flows are the same size, and then we force that with a wave field, and then just break the field of ice using some kind of breakup criterion, then update the marginalized zone, and then just iterate and use that as the geometry for the next iteration. And then we do that until we reach a steady state. And then what we found is that after quite a few breakup events, so here about 20, we reach a steady state. And again, we find this sort of modal distribution. So here we did not attempt to fit any particular parametric distribution to them, but clearly this is not a power law, it's modal. There's a model, there's a mode in the middle here. And this was consistent for all the experiments, the numerical experiments we did. So we clearly here, in all these cases I mentioned before, see the emergence of a mode in the distribution. And that's not a property of the power law. When Nico started his PhD with me a few years ago, the idea was to try to simplify the kind of model we consider the 3D scattering model and try to make it simpler. And so we went back to sort of a 2D model where we just have a nice field, and then it's just a reflection transmission process, basically. So we just have a one-dimensional ice field where wave propagates through a field of ice, and then we use standard linear wave theory for that. We also include some damping mechanism here. Sorry, I'm in the middle of something. Sorry, someone just entered the room here. Anyway, so yeah, we introduce a damping to make sure the waves damp quickly enough through the ice. and then try to replicate essentially the studies we did in 3D, but in 2D. But of course, that simplified things a great deal. So we were able to simulate a lot more cases and over a much larger extent. And so the idea is that here we consider an incident wave field with given amplitudes, period, and phase. And then we're able to simulate the associated strain fields through the ice cover here. And so then we can include a breakup parameterizations by having a critical strain in here, and then simulate the evolving breakup by starting from a very simple geometry, so one semi-infinite flow, and then it just keeps breaking up until it stops, essentially. So here the breakup criterion is based on a critical strain of about 10 to the minus 5, which was taken from empirical data. And here one assumption is that at each iteration, a flow can only break up once at one location, but multiple flows at each step can break. And this is a sample of the results we found. And you can see that we have, again, the emergence of these unimodal distributions here. So here are the results, I think, for monochromatic forcing, so just one frequency. And on the left is for different values of the breakage strain, and on the right is for different values of the ice thickness. And they have this very typical shape. So they are clearly skewed here on the right. And so first thing is clearly not a power law, but a distribution that fits very well is actually a log normal distribution. And here I'm not just showing you these results because they are the best ones we have. We have actually a lot more results, and consistently a log normal distribution fits really well. So not just for monochromatic forcing, but also for forcing caused by a wave spectrum. So here I refer you to our paper, which was recently published in the Cryosphere, where we discuss that in a lot more details and do a bit of sensitivity analysis as well. So, of course, there's still the data which have been analyzed under the formalism of power law from the start. So what about it? Well, we decided that to try ourselves to see what happens when we get our hands on one of these data sets and try a different functions to fit through. And so we contacted a bunch of people to try to get their data, and we managed to get some data here from Liu et al. So this original study was published in 2007, and we only analyzed here one image, which is 2,000 by 200 meters in dimensions, and it contained just over 2,000 flows. And the flow sizes ranged here from about 2.3 to 92 meters. And then we fitted a range of different functions here or distributions through this data set. So at the top here, you can see the histograms of the flow size distributions. And here at the bottom, it is a cumulative distribution. And here the different functions which were fitted are the ones considered in that original paper by Liu et al. So the Pareto, which is a power law, a truncated Pareto, which is a truncated power law, and then a Weibull distribution. And then we just added here the green curve, which is the log normal distribution. And as you can see in the top here, when we look at the densities, it does a much better job than the other distribution and captures the modes very nicely. But if you only look at the cumulative distribution at the bottom, it's not as clear that the log normal distribution does a good job. In particular, it seems like it overestimates the number of large flows. Now, one possible reason for that is that this is a fairly small size image that we analyzed, and therefore some of the large flows may have been on the boundaries of the image and we will not be able to capture them in the distribution. here. But at least our log normal distributions here did a really good job at capturing the modes. All right, now we did that for additional data. And here I'm not gonna get into the details of what data it is, but here are some of the results. Again, this is all done and all the credit should go to Nico for this analysis here. Consistently, when we compare the log normal fit with a Pareto or log normal distribution, the log normal seems to be superior and captures a consistent mode. Okay, so there is still this issue of why the log normal distribution would emerge here from this fragmentation process. I mean, I explained before that we can understand the power law through a cascade fragmentation approach here, but what about the log normal? Well, it turns out it's been figured out a long time that this can happen, and this is the Kolmogorov fragmentation theory from the 1940s here, and it works in a very simple way. And if you consider here a flow, so here I take a flow, but of course in the original paper here by Kolmogorov, they just took a, so it's not a nice flow, it's just a fragment of some kind of material which experience repeated fragmentation. But in our case here, if we take a flow of size d naught, and then the key thing is that now instead of breaking it in half or in n equal pieces, we break it at a random point. But it's not, this random point is not necessarily determined by a uniform distribution. It's actually an arbitrary distribution d here on the finite support 0, 1. But the point is that we break it at a random point, so now we obtain a flow of size d1, and then we just repeat, we keep doing that. And so we obtain this so-called multiplicative fragmentation process here, where the size after n steps is just a product of n random variables here. And then when we take a log of that, then we can use the central limit theorem to say that the log of dn, so the log on the right-hand side here translates into a sum. So it's a sum of random variables, and using the central limit theorem, it tells you that the log of dn is normally distributed, or dn is log normally distributed. So that's a really nice theoretical argument here to show the emergence of the log normal distribution. So this approach here I just mentioned is very qualitative. So we wanted to take it a bit further and see if we could explain it in a more quantitative manner. And it's very preliminary what I'm mentioning here. It's more a framework than an actual model for the breakup of flow size. But there is actually a stochastic process known as geometric Brenner motion, which can be used to actually generate this log normal distribution. And the way it works is that essentially you have, so in our case would be a flow of size L, but which evolves continuously with time, but in a stochastic fashion. And the way it evolves is based on this very simple exponential decay model here, but the decay rate kt here is actually a number which evolves in time and contains a random Gaussian noise parameter in there. And then when we work with that, so this would be the stochastic differential equation, then we're able to derive, so there's a whole theory for that, we're able to derive an associated Fokker-Planck equation, which describes the probability density function of flow size. And it satisfies this now deterministic equation, which can be solved analytically. And the solution is exactly a log normal distribution. Now it has parameters which evolves in time, okay, and it's unclear how to interpret this parameter in the context of the breakup of sea ice due to a wave event, but it emerges naturally from this very simple stochastic process. FL here is a time evolving log normal distribution. So of course, this is nice, but this probably raises more questions than it answers. So, could could we come up with a parameterization of this repeated fragmentation process in the context of this stochastic process here that could be integrated into a flow size distribution evolution model, such as the one that Cecilia Bitz talked yesterday that is currently in size. So it's unclear how we can do that. And even if we could, how do we actually relate the parameters of that process to the underlying physics causing the fragmentation? And how do we even turn on or off that process, given that it's very likely a short-lived process? So the way what I'm thinking about here is that there is a wave event which is short-lived and breaks up the ice. So how do you turn it on and then turn it off? So that would be questions to answer. But yeah, so I raised some of this issue here in our recent papers. So published in Philosophical Transactions A. So if you want to learn more, then please have a look at that. All right, so just to conclude here, so I want to emphasize that we have consistently here been able to find the emergence of a log normal distribution as opposed to a power law in not just in one case, but in a range of different settings. So we saw it emerges from simulations of wave-induced breakup in a deterministic model of wave ice interactions. We also found it in some data. Now, we only look at a few of them. So of course, there's a lot more to do here to see if it applies in more cases. And we also see that it could be understood as emerging from a stochastic process of repeated fragmentation. Of course, there's still a lot we don't know. So the extent to which this log normal distribution holds, now we don't expect it will hold in all cases and over a wide range of flow size, especially larger flows. It's not clear what would happen there. So there's more work to be done there. And it's also very not clear how to actually parameterize a log normal distribution in a flow size distribution resolving sea ice model. So there's more work to be done here. Yeah, I'll stop here. Thanks.
Yeah, thanks again, Fabien.
Thank you.
Yeah, perfect timing. So we have time for 1 or 2 quick questions from the audience here or anyone on Zoom. Oh, yes, please.
Thanks very much for the very nice and interesting presentation. And this is Training Dan. I was wondering, what was the largest data set has been tested here? Thank you.
Largest, do you mean largest in terms of number of flows or flow size?
Number of flows. Like, so you had the first experiment saying about 2,000 flows.
Yes.
And then you also mentioned some other data sets.
Right.
I was wondering what's the largest number of flows kind of.
Yeah, no, I understand the question. Yeah.
Thank you.
Oh, okay. So it's on the figure, I believe. So let's go back. Okay. Oh, there we go. So here you got 2,300, then here 26,000. So yes, that one will be the highest here, nearly 27,000.
Oh, thank you.
Hi, thanks for the talk. This is Cecilia Bitz, and I'm curious if you should or if you don't need to consider other processes that affect the flow size distribution, such as deformation, mechanical deformation that might cause fracturing. Also, the welding process. How would those change your problem?
So yeah, so the original motivation for all this work is the wave-induced breakup, definitely. Now, in the stochastic process here I mentioned, so I mean, there's nothing that says that it has to be only waves, right? So other processes could be thought about as part of that process as well. Now making a direct relationship between actual physical process here and these kind of models, I'm not sure. And I still believe that the current modeling approach based on the flow size distribution model by Chris Horvath is definitely, the best thing that can be done right now. But another motivations here for looking at this kind of stochastic models is that there has been recently an attempt to look at a stochastic process to describe ice thickness distribution. Now, as far as I'm aware, there's only one paper on that that was published a few years ago, and I'm sorry, I forgot the name of the authors. And I don't believe it has been really embraced by the community. I think it was published in one of the physical review journals. But we wanted to see if there was something that could be done along those lines for the flow size. Now, to answer the question about how to include this kind of other processes in this modeling frameworks, I'm not sure. I'm not even sure how to include waves in this kind of modeling framework.
Okay, yeah, thanks again, Fabien. Cecilia kindly put the name in the chat. Yeah. And we'll see you soon in Dunedin. Yeah, thanks, Fabien.
Oh,
Yep.
awesome.